Okay, so we want to solve this problem. In the design of a timing mechanism, the motion of point B, okay, is fixed in the fixed circular slot and is controlled by guide A. Guide A, and this is pin P, which starts from rest with pin P at the lowest point in the circular slot and accelerates upwards at a constant rate until it reaches the speed of 175 millimeters per second at the halfway point of its vertical displacement. The guide then decelerates at a constant rate and comes to stop with pin P at the uppermost point in the circular slot. Determine the n and t components of acceleration of point P once the pin has traveled 30 degrees around the slot from the starting position. Okay, so in this problem, the pin P is traveling in a circular slot, so we can express the position vector of point P either in cylindrical or polar coordinates or in the Serifine basis. No much difference between the two bases. I mean, the vectors are different, but the difficulty or the analysis is kind of the same when using the two bases. So we can use the polar basis, and if you want to use the Serifine basis, that's a simple transition. So we can use the polar basis to describe the motion of the pin inside the circular slot. So I'll take my origin to be here, the center of the circular path, and then I can draw ER this way and E theta perpendicular to it. Okay, and let me draw also my Cartesian basis. I'll draw EX like this and EY like this, and this is the angle theta. So then I have that EX, EY, when rotated by an angle theta about EZ, gives us the polar basis. Now we could have taken the basis, the Cartesian basis, to be like this, for example, a regular EX, EY horizontal and vertical. And then if ER is as it was originally, or if ER is like this, ER, E theta, then this is the angle theta, always starting from EX to ER. And in this case, because we're going clockwise, theta is going to be negative. So they would have different values. And this one, in the top figure, it's positive. In the bottom figure, theta is negative. So let's stick to the first one I drew. The second one is not wrong, but it's slightly different. Okay. So I can write the position vector of the pin P in polar coordinates. Why not cylindrical? Why just polar? Because the motion is planar here. Because the pin is moving on a circle which with constant radius, then this term r dot is 0. So the velocity simplifies to r theta dot e theta. And the acceleration similarly for r is constant, these terms go away. I'm left with minus r theta dot squared ER plus r theta double dot E theta. And basically what this problem is asking for is for the acceleration of pin P once the pin has traveled a certain distance. Okay, so what we want to determine is the acceleration of pin P. So I have more information about the kinematics of pin P, which is basically that P is also in this slot A, the pink slot. So then the vertical motion of the pin slot needs to correspond to the vertical motion of the pin P, because pin P can move horizontally inside the slot, but vertically it has to match the its vertical motion has to match the motion of the slot, the vertical motion of the slot. So basically, I know that v dot ex, so that's projecting along the vertical, because remember ex is vertically down, which is r theta dot, well, may remember, er is cosine theta ex plus sine theta ey. E theta is minus sine theta ex plus cosine theta ey. So now E theta dot Ex is gonna be equal to minus sine theta. That's gonna be equal to X dot, the vertical velocity of the slot. So for the slot, for AV is X dot Ex and A is X double dot Ex. Now, okay, a common or a question I would expect is, why didn't I put a minus sign for the velocity? V is minus x dot ex. Well, I'll just take v is x dot ex, and then if I'm moving upwards, I'll just have x dot be negative. So I'm moving upwards, I'm moving in minus ex, my velocity is going to be negative. So no big deal, this x dot can be negative. Okay, so then I have this equation relating r theta dot theta and x dot. So what is known here? R is known, theta dot is unknown, theta is known. They tell us to find the acceleration at a certain distance or at a certain angle from the kind of starting position. Sorry. And then x dot is unknown. We're given actually x dot at this location and x dot at this location, which is 0. X dot is 0 here. And x dot is 0.175 meters per second here. And in between the two, x double dot is constant. And then here, x dot goes back to 0. And in between the middle and the top, also the acceleration is constant. So I have a bunch of unknowns. 2 unknowns, 1 scalar equation, so I'll need to look for more equations. But I remember that also the acceleration of A in the EX direction, the acceleration of P in the EX direction should match the vertical acceleration of the pin A. So A dot Ex is minus R theta dot squared. ER dot Ex is cosine theta. And then E theta dot Ex is minus sine theta. So minus R theta double dot sine theta. That should be X double dot. Okay, and that's another equation. Let us count our what's known and what's unknown. Okay, so R is known, theta dot again is an unknown, theta is known, theta double dot is an unknown, theta is known, and X double dot. So our unknowns are many. Theta dot, theta double dot, X dot, and X double dot. Okay. So 2 equations for unknowns. We need to look at more data. I think what we should look at right now is basically X dot and X double dot. Based on the information that X dot is 0 at this angle initially, and then so X dot is 0 at this angle initially, and then it goes to 0.175 meters per second at a constant acceleration. Let us see. Initially, note that initially here, the angle is 20 degrees, kind of like symmetric to the top. So initially, when we're at rest, theta is not 0, it's equal to 20 degrees. So X dot, okay. So X dot of 20 degrees, so when theta is equal to 20 degrees, is equal to 0. And X dot, when theta is equal to 90, that's in the middle position, when we have EX and EY like this, and then ER and E theta like this. So the angle theta is 90. When theta is equal to 90 degrees, is equal to 0.175 meters per second. And then here, at theta is equal to 90 degrees, x is 0. We're at the same horizontal level as the origin. Whereas when x is 20 degrees, when theta is 20 degrees, x is this distance, which is just r, the radius, cosine theta. 0.25 cosine 20 degrees. Okay. Meters. So now I have the velocities at 2 points, and I know that x double dot is constant. Can I determine x double dot? Well, usually what I would think about is that x double dot is dx dot by dt. And because x double dot is constant, I can say that dx dot is equal to x double dot dt, and then I can integrate, taking x double dot outside the integral because it's constant, and I'll get the delta x dot is x double dot delta t. So x double dot is delta x dot over delta t. And then I would be able to calculate x double dot. Except that here, I'm not given time. So I know delta x dot, but I do not know time. Sorry, the pen is a little bit annoying. So I know delta x dot, but I do not know delta t. Fortunately, so this will not work. Fortunately, there is a relationship between the acceleration, the position, and the velocity, which is going to be useful because we have these three quantities. Remember that x double dot is dx dot by dt, and I can use the chain rule, dx dot by dx by dt. That's for the rectilinear motion of the slot A, and that's x dot. So I'll get that x double dot is x dot dx dot by dt. By dx. Okay, so x double dot dx is equal to x dot dx dot, and now I can integrate. X double dot is some constant outside the integral, and x goes from 0.25 cosine 20 degrees to 0 dx, and then x dot goes from 0 to 0.175 x dot dx dot. Okay, so then I can solve for x double dot. So I figured out one of my two unknowns, which is x double dot. Okay. And then using the same equation, I can figure out another unknown, which is x dot. So now, if instead of integrating between the two initial position and the middle position, where we know the velocity of both, let us integrate to the point where the pin has traveled 30 degrees, at which we want to find the acceleration of the pin. So this point, say here, this angle is 30 degrees. So we've traveled 30 degrees. So the total angle theta is 50 degrees. So I want to find x dot when theta is equal to 50 degrees. Okay. Um, and when theta is equal to 50 degrees, x is just r cosine 50. Similarly to when we found x is r cosine 20 for at this location, r cosine 50 gives us the x coordinate of when the pin is at this location. I'm sorry, the figure is crowded. X when theta is equal to 50 degrees is just 0.25 cosine 50. So now I integrate. I'm gonna copy starting from the same step. X double dot, which we just found, the integral from the initial point to x is equal to 0.25 cosine 50 dx is equal to the integral from 0 x dot dx, and here dx dot, and here that's what we want to find, x dot when theta is equal to 50 degrees. Okay, since I'm using x dot at the boundaries, let me change the name of the variable so I can find x dot. Okay, once I find x dot, then I have two unknowns. So basically, I found two unknowns. So basically, two out of the four. So basically, I'm left with two unknowns with the two equations, 1 and 2. So now I can solve for theta dot, theta double dot from 1 and 2. And once I know all these quantities, I can solve for the acceleration. Then I can calculate the acceleration of the pin when theta is equal to 50 degrees. Okay. By just solving these two equations, 1, 2. Okay, great, thank you.